Thanks for coming, everyone, to the inaugural IDE seminar of the semester. Today, we're really excited to welcome Professor Chenhao Tan. He's an assistant professor of computer science and data science at the University of Chicago and is also affiliated with the Harris School of Public Policy. His research interests include human-centered AI, NLP, and computational social science. And today, he'll be talking to us about human-centered AI, how we can understand and improve decision-making through explanations. So without further ado, please take it away, Professor Tan.
Oh, thank you so much for the invitation. I didn't know it's the inaugural one, so I guess it's a great honor and I'm happy to be. Thank you for coming. So this is a talk about human AI. So one path of developing AI is to keep pushing and make AI bigger and stronger in the pursuit of quote-unquote intelligence. And I guess, however, the term intelligence can be heavily underspecified, and as a result, we may get to a world that's similar to the movie Matrix, and all humans are being used as batteries. And hopefully you agree with me that this is not a world that we want to be in. So an alternative path is to develop AI that takes into account of humans, so that AI it can empower people and benefit humanity. And here is a book cover of a book titled Human-Centered AI by Ben Schneiderman. And I guess like it's kind of entirely on the theme, so it's kind of a plug, free plug for his book. But more importantly, I kind of want to point out that in this picture, somehow AI is not very visible. And I guess that's, in a way, an ideal world where AI is a successful technology when it's not as visible as the previous one. And that's kind of the goal of the entire research agenda. And here I'm going to focus on a particular perspective that has been driving a lot of my research, where I think it's useful to think of human as an incomplete puzzle, where we are trying to figure out the shape of the puzzle, and then we can build AI so that AI can fill in the missing piece, and so that it can complete the puzzle. And that will be kind of the central theme of this talk. So in this talk, we're kind of going to focus on a very somewhat narrow setting, but I will kind of argue it's still a very important setting where we are going to think about how we can effectively develop AI to support human in decision making. So to make sure we're on the same page, let's start with what I mean by decisions. So by decisions, I mean this, like in a way, very simple categorical decisions. A judge sees a person and deciding whether this person can be bailed or not. And in New York law, actually specifically requires the judges to make a prediction about whether the person will commit a crime or not if they are bailed. And that's the main criterion for making the decision. And the second example is if you see a chest X-ray and maybe you are going to decide whether this person has pneumonia or has COVID, and it will be a yes/no decision given this image. And finally, it will be a hiring or admission decision where you see a person's application and you decide whether to interview or whether to admit the student. And usually the decision is conditional on this prediction of how well the person is going to do if they join the university or join the company. By the way, feel free to interrupt me anytime with questions. Happy to go through anything in more detail. So in general, I think like, if you are interested in this kind of problems, you can check out this article. I think this kind of decision is actually very prevalent in a wide range of settings, and you can call them like prediction policy problems. And two important characteristics that kind of guides this line of work is first, humans should be in charge. Because of a lot of reasons related to accountability, law, and ethics. And that's why, like, even if AI is very good, we still want to use AI as an assistant and make sure a human is the person who makes the final decisions. And here is kind of one example of like specific law that requires this. This conclusion at a case at the Supreme Court of Wisconsin concludes that a compass risk assessment should not be used to determine the severity of a sentence or whether an offender is incarcerated. And judges be made aware of the limitations of risk assessment tools. So a lot of what I'm going to talk about later in the class presentations, you can think of them as ways to help judges or to help decision makers become aware of the limitations. And second, in a lot of these decisions, I think this is somewhat obvious for social scientists, but it's kind of new to computer scientists. Right? Like humans' decisions are far from perfect. High-stake decisions often like involve reasoning about these complicated processes with inherent uncertainty. So it's not like I'm just looking at whether you can recognize a dog in your image, whether it can drive, is very different to these scenarios where you are trying to build systems to simulate or emulate human intelligence. And as a corollary, humans have mechanisms and biases and preferences in decision making. I added preferences so that later I can talk about RLHF and OpenAI stuff. But I think most of this, you just need to think of the mechanism and biases for the sake of the talk. And just to emphasize this, like to remind you of the metaphor that I've been saying, human decisions are far from perfect, and it's useful to kind of put this in your mind. Like we are looking at a puzzle, and we need to figure out the shape of the puzzle. So because of this, there are also ripe opportunities for AI assistance. Humans are not that good, so the bar for improving human is actually very low, and we'll see that too. And this talk, we are going to focus on a particular way to improve human decision making, where we are going to use explanations. And later, I will make clear what I mean by explanations, but for now, conceptually, you can think of you have a black box AI, and it will generate a message, and that message will take many forms, and that will be explanations. And we show this message to people. And typically, many studies, including mine, will make the hypothesis that explanations may help humans make sense of AI predictions and improve their decision making. What I'm going to highlight is that this sentence itself is problematic, but it is kind of very natural. As I said, I can say it confidently and write that as a hypothesis. But like I will return to this sentence in more details later. What's that question? Another thing I want to kind of point out right now is that most algorithms for generating explanations kind of ignore the humans in this picture. They kind of like, you must have heard of the phrase opening the black box. So the only input is the black box. And of course, this is simplified. And given the black box, I'm going to develop some algorithms. For instance, the line would perturb the algorithm in a certain neighborhood and then generate a proxy and output that as explanations. And there are many similar algorithms from many different algorithms, but all of them share this property. Well, the goal is to open the black box. So we only look at the black box. And the key message that I'm going to go over is that the second step is actually very important. Here I call it interpretation. And in order to have effective collaboration or effective AI, human AI decision making, we need to incorporate this interpretation step. And then we are going to kind of go through three parts. First, we are going to just show a quick evaluation to convince you, hopefully, that connect you with the current state of the utility of explanations. And then we are going to share a theoretical framework for AI explanation and human understanding. And then finally, we are going to kind of show a new empirical study to show that by aligning AI explanations with human intuitions, we can achieve better decision support. So let's start with the first evaluation. So this is a relatively kind of old work by CS standard, but I guess like social science again read like older papers, so hopefully you can still go back and read this paper. And in this paper, we look at this task where I'm going to set up the task. This task is your task as a decision maker. Imagine you are a Yelp reader, you go to Yelp, you read a review, but you somehow have the prior that deceptive reviews are very common on Yelp. You want to figure out whether a review is deceptive or not. And by deceptive, I mean it's written by someone that imagined this experience. Someone who has never stayed at the hotel, who just made this entire thing up. And a genuine review means that this person actually stayed there and paid for it and write a review on TripAdvisor. And I'm going to read this review out, and then I'm going to ask you whether this one is genuine or deceptive or not, and try as hard as you can over the next 1 minute. My stay at the Talbot was a wonderful experience. The service at this upscale hotel was beyond my expectations. The Gold Coast location is close to Michigan Avenue, the museums, and many of the other sites Chicago has to offer. If you are visiting Chicago, I highly recommend the Talbot. Raise your hand if you think this is genuine review written by someone who stayed at that hotel. Raise your hand if you. Oh, good. Yes, like if you think it's yeah. Oh, you are highly encouraged to vote. And yeah, raise your hand if you think this is genuine. Okay, I got like 2 or 3. Anyway, raise your hand if you think it's deceptive. I got 1, like, I guess. You are good. But let's see whether you are actually good. So now I'm showing you the explanations. So these are the words that an algorithm considers is important in making the prediction of whether this review is deceptive or not. C in the explanation, has that changed your decision? Like raise your hand if your decision got changed because of C in the explanations. No one? That's good. That's kind of the point too. All right. So the next one, this is another type of explanation. I show you 2 examples. You are not really supposed to read it, but I hope like the takeaway is similar to the previous one. These are unlikely to change your decision. Just as before I move on, this review is indeed deceptive. So I guess you are all slow, so you are great at this task. But we can try more examples, and I can try to convince you are not great in this task. But anyway, so this task, in this study, we developed a spectrum between full human agency and full automation, where we kind of designed all these different interventions. I'm not going to go through all the interventions, but you have seen the 2 most important interventions that I showed just now. And we look at human performance and trust. The only thing I'm going to highlight here is human performance. By default, human is terrible in this task. They essentially get about a chance performance, 50%. AI can actually do very well in this task. They can get about 87%. And similar to what we just saw, if we show people these feature-based explanations by highlighting these words that are important for AI prediction, human performance only changed very slightly. But technically, it got improved by the explanations. And if we show you the predicted label, that is what drives most of the improvement. And we can improve human performance by a huge margin, about 20%. But if you compare that to AI, then it feels not enough because there's still a big gap between human performance and AI performance. So that is kind of a quick overview of the current state of this. And the main kind of claim that I want to make here is human plus AI is worse than AI. Yes.
Just to clarify, when they're showing the predicted label, if they just follow the AI, they would get 87%?
Yes. If they just follow the AI, they will get 87. And they will choose not to follow certain times, and they tend to choose it wrong.
Okay.
And that's exactly the message. And I guess like I was just having a conversation with Thomas Maron, and I guess there's some difference in the existing literature, but I would say there is a big number of papers that kind of shows very similar results in a big variety of settings beyond the deceptive review task. And I think that one extreme that I can come back to later. And the general message is that human plus AI is performing worse than AI. And that is something we are going to kind of try to wrestle with and try to think about why this is the case. And the answer will hopefully be obvious after I explain it. And if you're interested in this set of papers, you can check out the survey paper that we wrote. We also had a kind of tutorial on how to conduct study in this space in collaboration with some psychologists like Tanya Lombroso. I guess I'm highlighting Tanya because she's kind of the main scholar about explanations these days in the world. Okay, so just to establish the fact again, so the main message I want to send is that human plus AI is worse than AI, and hopefully we all agree, ideally we want to get a scenario where human plus AI is better than either human alone or AI alone. And most of this talk is about why that is hard and how we can kind of get closer to that. Yes?
So are there particular kind of decisions where AI is better than human plus AI, or it's just the general blanket?
Yeah, that's a very good point, right? I think like the question is what kind of decisions this happen, and I think it would be great to have a very nice task taxonomy or ontology, maybe too much, but some kind of task definition to distinguish different cases. But here, as I'm showing this image, where the premise of AI-assisted decision making is usually AI is actually decent. And that means like AI outperforms human in some standard test benchmarks. And that is kind of pretty common in this bail decision and medical diagnosis. And in those cases, this scenario happens. Okay, so now we have seen the first part. Hopefully, you have kind of get on the same page. Current explanations do not have a very strong utility to improve human decision making. Next, we are going to kind of think about why. So this paper is titled Machine Explanations and the Human Understanding. This journal work with Cha-Cha Chen, Amir Sharma, and Shifeng. And so we have seen so far with feature importance, we kind of suboptimal outcome. But in the very early work in explanations, people actually have shown that feature importance can improve model debugging. And why do we see such mixed results? And that's kind of the main goal of this part of the talk. So in order to make sense of the current results, I think there are two questions we need to think about. First, like what are we seeing in those results? And the first part I'm going to explain that we're actually seeing very different constructs in those two mixed results. And then under what conditions can explanations improve human understanding? So first, like we kind of went through, as part of our survey work, we already went through these studies, and we identified most of the existing papers are concerned with three core concepts of human understanding. First, we want to see in the simplified problem, we have some pluses and minuses. We are interested in this task decision boundary, like what actually happens in the task. In the previous case, what actually makes a deceptive review, what are embedding decisions, what characteristics define someone who should be bailed. And then we often have this model decision boundary, which is the model that we learned, which can be different from the task itself. And then model error, and which are these yellow regions that kind of defines their intersections. And all existing quantitative measures of human understanding can map to one of these three concepts. And for example, in the deceptive review example that I just showed, it can be seen as measuring human understanding of task decision boundary. So the typical way that people do it is to measure human plus AI performance. And another set of studies that people usually do is to see whether humans can simulate the model prediction. So it's sometimes called human simulatability. And that's actually measuring human understanding of model decision boundary. And finally, there are also work on measuring trust, and that's concerned with model error. And just before I move on, it's kind of useful to point out that in the model debugging case, usually what you are concerned with is model decision boundary. And in the decision-making case, usually you are concerned with task decision boundary. So they are actually about constructs of different nature, and that's why we are seeing different outcomes. And next, we are going to formalize this and try to have a formal language to describe this. So to go forward, let's just stay with the local case. By local case, I mean we have a single instance X we are interested in, and there exists this Y variable, which is a true label of this case. So what is defined by the task decision boundary. And we also have Y hat, which is what the model predicts for this instance. And that's defined by model decision boundary. So Y will use F to define the function, Y hat we're going to use G. And Z is the model error, and usually the natural causal graph is to argue that you have Y and Y hat, and then they cause the model error. And what we need to wrestle with, or we need to really think about, is what happens in humans' mind. So we added this human understanding of them by adding a superscript h on top of these variables. So for instance, YH refers to human understanding of the label or the task label for this instance. And because these are all in your mind, so we don't really know their relation, so they are all kind of connected with these dashed lines. And the argument is that we need to think about how we hope they connect with each other and how we can design different interventions to shape their relations. So let's start with simple cases where we don't have explanations. And this graph is big, so we are going to zoom into this part where I kind of introduce the main language we have. So the main thing that we have is to define this show operator in causal graph. And show, what it does, literally in the predict label case, it means that I show you the predict label. And hopefully you're a rational person, we assume that you're a rational person, by seeing Y hat, you are going to set Y hat to be the same as Y hat H. And as a result, you have access to the model predict label. And another part that we are doing that's somewhat unorthodox, but I think that's somewhat necessary in this kind of analysis, is what happens with show is that we're going to redefine the relationship between variables in this graph. It will introduce new causal links between variables. And in this case, I'm showing the most simple case. We also show y. And show y is very unnatural in most cases because usually you don't assume humans have the y label. But in a wider range of cases that computer scientists care about, for instance, you are predicting the sentiment of review. You can kind of assume that a human reading the review knows the sentiment, although they may not know whether it's deceptive or not. And in that case, then you can also have show y showing up. Then show y will set yh to be the same as y. And as a result, the human will naturally know whether the model made an error or not in this case. Like this causal graph just describes a very simple case where you know the true label of this instance. And upon seeing the predicted label of the model, you know whether the model is correct or wrong. And then with that, we are kind of going to start to think about the role explanations. So we have the theorem in the paper, and I'm just going to read it quickly and then provide the natural language version of this. So when predicted labels are shown, for instance, X explanation E that's derived from only G, which is the model, cannot improve human understanding of task decision boundary or model error. That is increasing the correlation between Y and YH, or the correlation between Z and OZH, beyond the improvement from showing predicted labels. This is quite a mouthful, so I'm going to kind of just simplify the language and try to show them with more pictorial language. But the main claim is just to show exactly the separation of what we saw earlier without assumptions about task-specific human intuitions. Explanations can improve human understanding of model decision boundary, but not task decision boundary or model error. And in fact, in binary problems, the other two are equivalent. So to set up the kind of intuition of these statements, first we need to go back to the earlier picture. If we look at existing explanations, they are mostly generated from AI, or they are in the form of like opening the black box. So as a result, it means that the explanation function EG is only derived from G. So there is an arrow from G to EG, and there's no other parent of EG. That's kind of one of the key assumptions that we're going to make. And as a result, this kind of, if we show explanations to people, and so like we have, this is the graph because we need to read them about y hat h. So this is the first time that they need to show up in the same image. And you see this orange path between y hat and y hat h introduced by showing G, showing the explanation. Because explanation has this back path through the explanation function to the actual model function. Then by seeing the explanation, you know a little bit more of how the model works. And then as a result, you know what the model would have predicted for this case. And that kind of connects with the existing results that feature importance can improve model debugging. So by seeing, if you assume that you know where the true labels are, by seeing some of the feature importance, you can kind of judge whether the model is doing the right thing or not. And that can help you debug because you learn the model decision boundary by seeing the explanations. In contrast, if I show explanations in the case where I show you y hat. So this is another important part of the theorem. We need to show you y hat, which is the model's prediction. And in this case, if we don't make any assumptions about human intuition and explanations, then it cannot improve human understanding of task decision boundary and model error beyond y hat. That's kind of another important part of the theorem. So the reason is that if you look at the causal graph, G only has an edge to EG, or a connection between E and the rest of the true Y and Z is really only G. So as a result, E and Y and Z are independent given G and X by this separation. So essentially, like if you given X and G and Y, this part is blocked, and E has no relation with Y and Z. So as a result, in this case, E cannot improve the understanding of Y and Z beyond Y hat. And in order for that to happen, E needs to introduce new pathways in this causal graph. For instance, like E can activate certain human intuitions that was not there in the previous case before E was shown. And that human intuition is somehow connected with Z. And that can create this new pathway between model error, ZH and Z, between human understanding of model error and model error, and as a result, improve human decision making.
Can you just clarify quickly? So like the squares here are the latent variables and the circles are the observables, right?
The gray circles are observables.
Okay, and then everything else is just latent.
Yeah, everything else.
So what's the difference between a square and a circle and a diamond here?
A square is a function.
Uh-huh.
So like this is something that's like this a little unorthodox, but it's okay. Like I can go into more details maybe offline. But essentially, the square is just saying that y hat is gx. G is the model, right? So these are functions. They are really easy to understand. The only diamond is human intuition, because the human intuition is this mystical thing that I need to introduce like more additional operation to formalize it as a variable. But for the context of talk, you can just think of this as you can treat it the same as a circle for the context of talk, but because it's not really a variable, so we introduce it as a diamond. But like I'll go through this. That was like formal language that I think is useful, and I highly read it. But I think it is useful to introduce like a relatively straightforward example to go through the key intuition behind that. Imagine we are looking at this X-ray and trying to make COVID diagnosis. Essentially, I'm considering two extreme cases. Or like the second one is not extreme, but the first one is very extreme. It doesn't happen usually, but you can assume that it happens. The first one is user has no task-specific intuitions. And the right way to think about it is that you think you have an alien who is the first time on the Earth, who is the first time seeing any chest X-ray. So essentially, it's just a black and white pixel to this alien. And here I'm showing you some explanations, which are those two red boxes. And these are the pixels or the areas that AI is basing their predictions on. But showing the explanations do not really make any difference to this alien, because these regions do not mean anything to this alien. Because we, like going back to the earlier language, because we assume that there's no connection between the explanation and task-specific intuitions. So showing explanations really doesn't make any difference in terms of making prediction for the task. So the understanding of task decision boundary is still bounded by the model decision boundary. For the alien, the best thing that it can do is to just follow the model prediction. And similar to the deceptive review example, like if you are truly an alien, if you are tasked to make that deceptive prediction, the only thing you can do, or the right thing to do, is just follow AI prediction without any additional information. In contrast, if we have a user that has task-specific intuition, and that's the final slide where the example pathway is about. So one possible mechanism is that humans knows what are valid regions to look at. If you have not seen any chest X-ray, like I'm making this very extreme, very simple, you can see that these two boxes are not even on the lungs. And they are on regions that should be relevant for any diagnosis related to lungs. So as a result, the humans can use that explanation to verify whether the model uses valid information. Note that like this is not something that the human could have done if we don't show the explanation. If we don't show the explanation, the human only sees the model prediction. It doesn't have any way to do anything about it. But if I show explanations, it activated this intuition that is in human's mind, but it was not active before showing the explanation. And then that intuition can potentially actually connect with the true model error, and as a result, it can improve human understanding. And hopefully, it can lead to a scenario where human plus AI is greater than AI. Hopefully, that like makes clear what I mean by the earlier causal graph. And the point is that if we go back to this statement, explanations may help human make sense of AI predictions and improve their decision making. But this statement of like making sense of AI predictions and improve their decision making actually can be very different things. The relationship can be quite complicated. Improving human decision making, you need to actually improve the understanding of the task, which is not something you could have done by just opening the black box. You need to introduce something additional to the explanation process so that it can actually connect with the decision making, and that is missing in the current paradigm of generating explanations. any questions.
Could this framework possibly be used also to evaluate whether humans have the task-specific intuitions that they need to make better decisions?
Yeah, exactly. I think a part of what I think how we should go forward in this paradigm is also like we should be more explicit about what specific intuition the humans are using, and then also some validate that ideally, and then like the best experimental design would be you show that humans indeed use the intuitions, then you show AI is working with those intuitions, and then with both going the right direction, human decision are improved. But I'm going to show a simplified version of that experiment in the next study. But I think in general, that's very hard to do, and that's kind of what I'm calling for people to work on in the end. Yes.
How human intuition is related to experience, training, the specific task. For example, in the COVID example, a medical expert in an epidemic could assume that have this intuition while general audience does not?
Yeah, exactly. I think that's like you can make, in some tasks, you can assume that general audience is actually more like the alien, then you shouldn't really expect to see improvement. And that's kind of like why I was showing the design review. Right? I think I was very naive when I ran the study. I kind of believed that explanations can help people make sense of AI predictions and improve their decision making. That's why I was running that study. But in that case, like I'm really running a study with alien, and it turns out alien doesn't follow AI predictions all the time, and I don't observe the most desirable improvement that I was hoping to see. Okay, actually there I want to add a meta comment. Like I think there's actually some study coming out from like Sloan and like economics at MIT on radiology recently. I think there are different ways to look at the result. If you look at the result, you can also think of that actually I improved human performance by 20%, which is a great win if your goal is to improve judge performance and improve policy outcomes. And I think that's totally valid, and I think that's a reasonable way to go forward as well. And for now, within the kind of this talk, I'm kind of assuming that only getting human plus AI greater than AI is a win, but that's not necessarily the case in other settings. Getting human plus AI better than human can be a big win in a lot of policy settings. Like you are literally improving people's lives if you can get that to work in practice. Yes.
Because one question about the mechanism on the last slide is like, if I understood correctly, you're saying the explanation can like help the human learn the joint distribution of signals, but you could also imagine that like this is an additional signal, and so like maybe the joint distribution between like the prediction and my own information is different if it tells me to look at an armpit versus the chest. Is there any way to tell like how to distinguish between these two mechanisms? I think both could lead to human plus AI being better than AI alone.
Yeah, I think that's very interesting. I think we can kind of think more, but I think most of that is kind of saying that the current state of art is that people don't even think about any mechanism of how explanations are improving human decisions. And like if you are doing what you suggested by articulating how you are hoping the explanation is improving human explanation, decision is already like a step forward, and that kind of opens up ways to evaluate how the improvement happens. That's exactly like what I'm advocating. And I think, yeah, I think it's a good time to move on to the next study. But just before I move on, I kind of want to highlight that this is actually like, there is many other concurrent work that kind of identify similar points. Like for instance, like this paper title is "In Search of Verifiability Explanations Really Enable Complementary Performance in AI-Advised Decision Making." And that paper makes a point of verifiability, which is one particular type of human intuition. And what our work as compared to this is mostly of this formal language to think about this. And you should check out this other awesome work too in this space. All right, so hopefully I convinced you that connecting explanations with task-specific intuitions is critical for improving decision making. So now I'm going to kind of show a case how we can do that. So this is a paper titled "Learning Human Compatible Representations for Case-Based Decision Support." Like if you know some of my other work, you know kind of I'm a natural language person, but That's why I started with disability review. But it's very hard to do the first step of articulating the mechanism of how humans may interact with explanations in natural language. So I'm switching gears and move to images in this example. And then the recipe that I'm advocating, first we need to articulate the mechanism, then we generate explanations that tailor to this mechanism. So let's go back to our favorite pneumonia example or COVID chest X-ray example. Let's say this is a task, this is an image you want to make a decision on and decide whether it's pneumonia or not. Now I give you AI prediction, AI says this is pneumonia. That seems like very limited help. That's why a lot of people want to work on explanations. And then one type of explanation can be example-based. And that's earlier, remember in the examples, when I show examples for the review, I don't even ask you to read it because that's very hard to decide what you should do with those examples. But in images, typically, the mechanism would be thinking about whether these two images are similar. So this would be a justification of the prediction. AI says, this is a similar example to this one. This one is pneumonia. And you can use that to decide whether to trust AI or not. And roughly, you would trust it if this image is indeed looks similar to the image. If you would distrust AI if this image doesn't look like the image by your eyes. So in order for this explanation to work, there are two preconditions. The first one, similarity between test example and justification is correlated with model error. So indeed, when they are similar, the model is more likely to be correct. And that's not the focus of this one. The focus of this work is the second point. Similarity to AI is aligned with similarity to human. What AI thinks similar should be similar to what a human would claim as similar. Otherwise, the explanation would be useless. Just to show you more clearly what I mean. So this imagine is actually real data point from our experiments. So this is a task that separates butterfly from moth. And these are the points that the AI model learned. So this is a very good model, almost completely separates these two classes. And we are looking at this test image. We are deciding whether this is butterfly or moth. And AI provided this as a justification because it's the nearest neighbor based on AI's representation. And the problem is that this one doesn't look like this at all. So as a human, maybe I look at this. Oh, the AI must be making a mistake. They don't look similar, so this is the wrong prediction. And that would be wrong because this is a correct prediction. The issue is that if we look at a human perception, so we build a model of human perception. I will explain how we build it later. If we build a human perception model based on human perception, this would be the nearest neighbor. And these two now looks much more similar. So the argument is that the issue lies in the AI explanation. The AI's similarity, AI's metric of similarity is different from human metric of similarity. And as a result, AI explanation won't be very useful in helping human make decisions in this case. So in this case, going back to the causal language or in natural language, in this case, explanations are directly derived from AI representations. The reason that explanations do not work, or the reason explanations do not speak to human intuitions, is that the AI representations are misaligned. And so we need to learn human compatible representations so that AI speaks in a language that humans can understand. That connects to human intuition. In this case, is just their similarity perception.
Is it that you want to represent the explanation in ways that are more human understandable, or you want to reframe the underlying AI model itself? Because those two things are very different, obviously.
Yes. I think in this case, what I actually want to do is just to align AI with human intuition in terms of the explanation part. But as a side effect, we did change the underlying AI model as well.
The reason I'm asking is because that might bring your 87 down as well. Because if in aligning with the human, you're introducing the errors that humans make into the model itself, right? So there's two tasks here. One is to classify well.
Yeah.
The other is to explain.
Yeah, in human understandable ways.
In human understandable ways.
Yeah.
And if you are improving the explanation by degrading the model, that's maybe strictly worse than improving the explanation while at least maintaining the performance of the model.
Yeah, that's a very good point. Like I'm going to introduce what we did in this work. In this work, I think we are lucky, like by aligning with human representations. Like so there's a question. Another way to paraphrase Sina's question is whether a human understandable model can do the task as well as AI.
Right.
In this case, it happens to be the case that it can.
Right.
So I think that's good news for us. And in general, I think the trade-off is actually unclear, right? If your goal is to have AI-assisted decision-making, if you can have a 90% model that's completely human, not understandable, then human can actually make more mistakes by getting assistance from the 90% model compared to an 85% model, but that's aligned with humans. And humans are more likely to effectively use that one, and you have potential to get. So like using our earlier numbers, it could be with this 90 model, you are getting 76. But with 85 model, you have the potential of getting 87. So
I guess all of this sort of like privileges the human decision maker. Like throughout,
yeah,
we're privileging the human decision maker.
yes,
But my guess is that, for instance, if you think about sort of EU law and application of AI, that there may be cases where every once in a while somebody sues under law and says, tell me why I didn't get my bank loan. And in those cases, you have to give an explanation. But really what you want to do is you want to maximize the accuracy of the model that is almost never interrogated by the human. Just every once in a while, it's got to provide an explanation to be legal.
exactly.
But what you really want to do is make sure that the accuracy of the model, like that's the prima facie burden. And then the explanation is sort of like the every once in a while we got to be able to provide an explanation thing. It's not like about combining human and AI decision making.
Yeah, exactly. I think I'm mostly talking about the case where you are trying to combine human and AI decision making, where humans are the final decision maker. And I think there are many cases where that's not the goal, and you have an automated system. Occasionally, you need to provide explanation, and as long as the explanation looks good, it doesn't have to be actually useful. And I think that kind of speaks to like there are many different use cases of explanation.
So in those cases, you might say, hey, you know what? Like, I'm not going to try to make an explanation where the underlying model changes in order to get to a more human understandable explanation.
Yeah.
I'm just going to sort of like, you know, not hand wave, but sort of make an explanation where I'm privileging the accuracy of the AI model by itself and leaving it as is.
Yeah, I think that's a totally valid choice. I think going back to like this AI explanation and then human, like I think a lot of this is about what's the goal of the interpretation.
Okay.
And the goal of the interpretation could be moot. Like I just want to show you something that is good enough. And that's a totally valid scenario as well. Yes.
So in the claim that you want to create this human plus AI is better than AI world, it sort of assumes that there are cases of this task where the human is better than the AI, right? So like that's the only way you can create a human plus AI is greater than AI in some sense.
Actually, that's a fun point. I had like a kind of long conversation with one of my PhD students on that. I think it's not like, I think a typical way, that's a very natural way to think about it. I think that's a standing literature. Like if you think of the final task, like human error and model error, AI error, and you need human error to have parts that's not within AI error. That's kind of what you are saying.
Yes.
But like based on the previous causal diagram, that doesn't have to strictly be the case, right? Like by showing explanations, what happens is that you do not only have model human error, you kind of activate an additional set of intuitions. Like for instance, like again, this may not happen in practice, but in this doctor example, say the AI happens to be only when AI makes mistakes, AI's region will be totally invalid. Then humans can be strictly worse than AI, but a human has this insight that by looking at this region, it will always correct the AI's prediction when the region is wrong.
The bias offsets these.
Yeah, then human AI can still get a better predictions, despite human strictly is a worse decision maker than AI.
So then, is it interesting then to look at which tasks sort of fall under that type of interaction between humans
Yeah.
versus those the one I described where humans are sometimes really good at some extreme tasks, but then bad at the main task, but then the AI is better at the main task.
Yeah. I think there are different ways that complementary clarity can happen, and even in the extreme case where like human is strictly worse than AI, in terms of decisions, right? Human can still potentially carry with AI and make better decisions. But again, like this doesn't naturally happen, and I haven't seen it happen in my own experiments. But I think conceptually it can happen. Yes.
Related to Sinan's question, is there literature about for example, the theoretical guarantee of when you transform the representation, the instances where you can maintain kind of the predictive accuracy and the conditions for it, or is your work or the current state of the art pretty much empirical on that kind of trade-off?
I personally don't know theoretical work on this yet, but I'd love to see them. I personally, but we did do. Okay, I'll quickly go through this study. But in this study, we did do some synthetic experiments, so that kind of touches on, like we tried to change human alignment and AI alignment, representation alignment, and we did see, at least empirically in all cases, even human alignment and AI alignment is very bad. We can still see. You can pretty much guarantee AI accuracy, but get better decision support. But here I'm just going to quickly go over. This is not that essential beyond the conceptual point. But the main idea is that now we learned that we need to also have human intuitions of similarity judgment. So we collected some human attributed judgments, kind of the first such data set for chest X-ray. For image, we get 2 references, and then we ask which reference is more similar to that image. And once we get such a data set, then we can introduce a new multitask learning framework so that the model not only does the classification, but also learns human perception. And in this case, it happens to be the case that the model can do prediction just as well. And then the main setup is to kind of look at these decision support settings that we are interested in. So we first have this neutral decision support. So given a test image, the explanation that we are going to show are 2 examples. The first one is nearest neighbor in the predicted class, then nearest neighbor in the other class. So we kind of ask AI to give you the best evidence it can give based on current representation, and let you judge which one is more trustworthy, or which one is more similar, and use that to decide the label for this test image.
What is the other class?
So in this case, it's pneumonia and not pneumonia.
Oh, I see.
This is binary, so it's other, but you can easily generalize this to like more classes. So we expanded this with 3 different representations. First, random. Second, AI. And then AI with human comparative representations. And we can see that our human comparative representations with the final bar and y-axis is accuracy. It's much better than the other 2, often more than 10% better. And the puzzling thing is that AI is actually worse than random in this one. Like somehow AI's nearest neighbor is very badly calibrated compared to human similarity judgment. To make sure that we are not like completely just a bug or something. So we also run another set of experiments. That's not the only reason we run this, but I think it kind of resolves that puzzle. We also tried this persuasive decision support, kind of related to Sinan's question. Like usually when I write a paper, I would argue that this is not a decision support that you should ever use, because it's kind of manipulation. I show you the nearest neighbor in the predicted class, and I show you the farthest neighbor in the other class. And this is totally designed to get you to predict this one. But it's a good way to validate our representation, see whether our representation can successfully lead you to this one. Then it means that our representation is aligned with human similarity judgment. So the same setup, and then if you run a result, indeed, like you can see y values all goes up, and in the butterfly versus mouse case, we almost completely get things that align with human judgment, like more than 95%. This is kind of like crazily good. And in this one, then AI performance is better than random, and it kind of shows that AI somehow learned pretty good representation in terms of classification. That's why AI does very well in prediction. But so as a result, its farthest neighbor is reasonably well calibrated, but its nearest neighbor is not very well calibrated without any additional modeling of human intuition.
And just to clarify, these are all human judgments given random AI or human compatible AI decision support?
Yes.
Okay.
Yes. Exactly. Yeah.
But so the AI here was it like adversarially trained, or could you have done that so like it got better than random over time?
The AI just out of the box. I guess like it definitely will vary with different random seeds and so on. But the AI is just like one particular AI we build. But like it's very standard setup. We build a standard vision model.
Following on Sanat's question, do you have a sense of where just following the AI totally would be on these?
Oh, it will be very good. AI gets like 94 in this one and 97 on this one. So the point, we don't show AI prediction in this experiment. These experiments are just about evaluating how good the decision support are. But that's a good point, and I guess that's a subtle point that I kind of have been avoiding. I will get back to later. But in general, like the short story is that actually achieving human plus AI better than AI or human is really hard in decision making. And I wouldn't claim that I figured out the complete recipe to do that yet.
But that's true in tasks where AI is very good.
Yeah, exactly, right? I don't think it's surprising. I think it's like, it's more of like the naive me 3 years ago was underestimating how hard that is. And now like I'm just like learning how hard it is.
Yeah. But I guess what I'm saying is that it may be the space of tasks, the region of the space of tasks in which AI is sort of bad, is maybe very fruitful that space for collaboration of human and AI, right? Because in some sense, what you want in both directions is AI teaches humans where humans make mistakes, and humans teach AI where AI typically makes mistakes.
Yeah. I think typically like when AI is bad, then like it's counterintuitive to hope that that will improve human decision making. As I said earlier, it could still happen.
No.
In that case, you can get a human to improve AI.
Right.
Exactly. But I think that is, or there's a lot of like work in machine learning that's kind of like, in a way, that's kind of all of machine learning work, right? You are trying to get a human to make AI from 0% to be able to do the variety of this task. Right? Does that make sense?
No, it does make sense, but I think if you think about this as an evolving process where it's not a static data set where you're just sort of like learning labels, but it's some sort of ongoing tasks where the inputs and the labels and the environment is dynamic, that an equilibrium of human plus AI faced with dynamic decisions and changing data and so on is sort of optimal, little o, where they are teaching each other, right?
Yeah.
It's not sort of like, oh, wow, AI is really bad at labeling. We're going to get humans to improve the AI label, right? At some point, it's going to get pretty good.
Yeah.
But humans might have some error in judgment that they can learn, oh, you know what, like once you teach AI a lot, it can learn some structure that's imperceptible to humans that it can teach humans in an explainable way.
Yes.
But this sort of doesn't make sense if the task is static, always the same. But let's say the task is, oh, this week it's the same task, but the inputs are very different. The world has changed, the data has changed, the dynamics have changed. Suddenly that equilibrium starts to look a lot more important than in these static tasks.
Yeah, exactly. I think that's exactly the vision, right? I think ideally you get this kind of co-evolution going on. And here you can kind of see that like we are kind of just evaluating this step where you get AI a little better than humans, or in some cases maybe 10% better by accuracy measure. Yeah. How you can transfer that knowledge to human. That's kind of the essence of explanation. That's why I agree, like maybe complementary is not really the goal. And the goal is to get a human to catch up to AI so that then you can kind of keep this co-evolution going. I think that's exactly right? I think this is about like thinking about what needs to happen so that I think like we are actually switching to the teaching angle as well. But I think part of the same principle applies that the explanations need to speak to human existing intuitions and figure out like which part is that you need to expand a little bit and how you can expand the human intuitions so that the human intuitions can grow. And that's kind of indeed like something that we also discussed in that more theoretical paper. Once you have human intuitions that's evolving over time, what you are hoping to see. And I totally agree, and I think that's like the long-term vision of like this whole line of work.
Especially if you think about the model as being endogenous, right?
Yeah.
You think that the human is building the prediction model, the
Yeah.
AI model, teaching humans something about protein folding that was never perceptible to humans by running AlphaFold.
Yeah.
Then the human might say, oh, well, now that I understand that, let me reprogram AlphaFold in a different way to capture some new dimensions that I had never even thought of, but I can unleash the machine on it now.
Yeah, I think that's totally like a great outcome. I think why a lot of people are interested in explanation is that right now that cannot really happen because like we don't quite know how to control this. We don't know what AlphaFold really does, and we also don't know how to get this new theory from AlphaFold. And those are all like good questions that actually like maybe I should just jump to future work quickly. Yes, go ahead.
Sort of in the same line, I was just curious about this. If you separate its explanation and interpretation, then even if we say that the model is fixed, like if we say the world is actually fixed, the way that the human uses the explanation that is interpretation is also going to change over time. I could imagine you'd have like if I'm a judge and I have to make decisions on cases and I get this tool that shows, okay, this should go one way or the other. Initially, I'll have some resistance to it, but I imagine over time that, oh, actually, the figure out it's quite good. And I'm likely just to speed up the process, I'll trust it more and more.
Yeah.
Is that something that's been, it seems like the setups you've been sort of exploring so far have been like single cases, people have been shown once, okay, this is a moth, this is a butterfly.
Yeah, I was talking to, go ahead.
Yeah, sorry, just if the same sort of experiment repeated with the same people, do they use it differently or?
Yeah, that's a great question. I think I was just talking with Mohammed. I think a lot of the current setups are in this kind of decision trial setting where like essentially similar to what I'm doing here, I'm showing here. But I think what you described is kind of a great direction. And I think like a lot of this can be thinking of like this feedback that you are giving, it's kind of building up human intuitions so that a human actually have some intuitions to leverage in this human AI interaction. I think there is relatively little work in that space, as far as I know. But again, I also think part of this could be that different disciplines are not talking to each other. But as to my best knowledge, I don't know a lot of that.
Okay, thanks.
Good. In the interest of time, I guess I'm just going to quickly. I have some RHF thing. Actually, this is very quick. I'm just going to make it. I like this point, so I'm going to explain it. So, like, most of you probably have heard of RHF. Roughly here, you are getting, like, say, in summarization, you get an AI model, LM, to generate two summaries and ask a human which one is better. And here, I'm also asking human which one is more similar. They look very similar in terms of the question that we ask, but I kind of want to point out they're actually very different. On the left, I'm trying to model human perception. And on the right, you are modeling human preferences. And that's kind of where the phrase that I'm trying to emphasize here. I think on the left, what I'm trying to get at is the mechanisms in human decision making. And typically in OpenAI, what you are getting at is human preferences. And of course, like the real OpenAI is probably more sophisticated than put in here. But if you only get human preferences, then you will be bounded by human understanding. And it also relates to the conversation with Sinan just now, right? And in practice, if we actually want to make progress in science, or like this high-stakes decision-making or policy or many other settings, well, preferences are not really going to get you anywhere. We need more than preferences. And we need to actually understand these mechanisms and biases in human decision-making. And that kind of guides to like what I think the future of humans and AI should have. First, like we need to advance series of human decision-making and interaction with AI. Kind of like open human brain in that sense. Then we hopefully reshape AI with new objectives, new data sets, and new algorithms, so that AI becomes kind of adapting to this new understanding of human. And then finally, in human AI interaction, we need to design and support effective interaction. And the explanations might be part of the answer, but explanations may not be part of the answer. Kind of that's, although this entire talk is about explanations, but I think in the future, the design space is much bigger than just explanations. And I think this is like very exciting future that like way beyond what I can personally work on. So I hope that more of you will be interested in these problems and think about these questions. And with that, actually, this is some one example I'm going to skip. With that, I guess I just want to thank all my collaborators, and I'm happy to take more questions.
Do you think the nature of explainability has changed with large language models? Like, whereas now, or like a lot of cognitive theories of human explanations is that first we come up with an idea and then we fabricate explanations that seem likely, and it seems that people are using language models in the same way, asking why do you say this, or why might I have this disease when people use it for like a WebMD, and those are not part of the decision necessarily, right? So do you think that the nature of explanations has changed with this?
Yeah, I think I get that question a lot. I think there are two parts of that question. Like the first one is that I think for this kind of decision-making setting that I'm interested in, like it's unclear large language model really changes things that much, since like they are not naturally good decision makers. Like they do seem very powerful, but compared to a model that's trained to do medical diagnosis or trained to do Bayesian decisions, I don't think it's actually like going to replace those in those settings. So it's not necessarily going to change that part. But I do think what it has is that you now do have these models that encode a lot of human intuitions. And they can potentially be used to, in conjunction with some other decision model, like we have some active project that we are thinking about, so that it can generate explanations that are more tailored to human intuitions, better tailored to human intuitions. I think there's a lot of promise there in that sense. I'm not seeing like work, okay, I think then there's the third part. I think for that, what I'm actually excited about, I think there's still a lot of work to be done. The third part I'm going to get at is that maybe this is what your question was asking, right? Like these large models can indeed already generate some good-looking explanations, and I think that part is more similar to what you were saying. They are similar to, like I had another kind of short paper. There's actually a lot of theory in psychology kind of says that generating explanation is just hard for humans. Right? It's very hard for a human to actually generate a good explanation, but it's easy for humans to generate a good-looking explanation. Like generating explanation that somehow makes you feel like you understand something about the problem. We can, like this happens just so much, like all of us probably have experience about this. I think LLMs can make that part easy. Unclear that is, like that can make you comfortable. Unclear that it can actually make it useful by definitions beyond comfortable. I think just to be clear, I think that's similar for human explanation as well, and I think that's what you were going into. And I think my position in the large language is actually very powerful, can change a lot of frontiers for many disciplines. Or many questions, yes.
Since you motivated this talk with the legal example, I wonder if you thought about kind of illegitimate and legitimate mechanisms for coming to a certain decision, and like trying to use these approaches to prompt people towards the like legitimate mechanisms.
Yeah, exactly. I think that's kind of the hope of this kind of work. Ideally, through this, we can kind of identify legitimate and illegitimate ones, and push people all the way to the more legitimate ones.
So how do you make sure the model learns the legitimate ones and not the illegitimate ones?
No, like the whole, like in the context of this talk, you can mostly think about is not really questioning about human judgment. It's more about illustrate mechanisms behind the model. That's kind of the goal of explanations. And the human intuitions can come in and judge which one is legitimate and which one is not legitimate, and use that information to make decisions. But as I said, like I think opening up the human one is probably the harder question. Like despite how hard it is to open the black box of AI, I think opening humans is actually the harder question. And that part is where it's very hard to make progress. Like I try to say that do something for the image setting, but like honestly, it's just hard to do it for other settings. And I think if you have like good mechanisms, good ways to articulate mechanisms in various like legal decision processes, that would be great. But like actually to make this concrete, right? Like the most clear legal mechanism maybe do not use gender or do not use race, or you have this 80% rule. But that's not really a mechanism. That's more of a constraint. And I think even in some settings like legal decisions, it's unclear what the mechanisms are actually for. Yeah.
So humans in human-centered AI is not a homogeneous entity because people are so different from each other. Now, you may provide an explanation, but some people might not like it. Have you ever encountered those cases where you have a very good decision support system, you made a decision in, let's say, public sector about distributing resources to people, but people just don't accept the explanation?
Yeah, totally. Like I think personally I don't work on personalization yet, but I think like for instance like there is this work called like algorithm nudge from Sanjog Misra at Booth, and like his main thing is about like there's this SNAP program in California where people need to sign up so that they can get food stamps, but most people don't sign up, and they send personalized messages, and they kind of show different messages can have very different effect on different people. And like that's kind of similar to personalization in search as well. I think certain level of personalization is probably like part of the future. It hasn't been like what I focus on in this report yet. Partly related to setup, like mostly I'm looking at decision trials, so I don't assume that I already have a lot of information about you. And that makes personalization hard. But I do think part of like some extent of personalization is probably critical. Yeah. Okay.
It's just a quick question, but like I feel like also the social, like there's a lot of like social factors that play into people like actually listening to these explanations. I remember my advisor she worked on expert systems in the 90s, and they had these which were like AI at that time, and they gave it to doctors, and they just hated using these systems because not because they were bad, they were actually really good. But just because they hated that there was an AI system that was supposed to be smarter than them, they just, and I feel like there could be a lot of these boundaries too. I don't know in the examples that you showed how many of them are actually expert users using the systems, but I could imagine like there's also some kind of sense of hierarchy that plays into all of a sudden like top down, like you have to work with this model. So.
Yeah, I totally agree. And I think like there's like in general, like making this broader system, is a lot more complicated. And I think like this talk was mostly about carving out a small part where like I can hopefully logically reason. And I do think like there is just like very blatant phenomenon that this interpretation step is kind of completely missing in the current approaches to general explanations. That's kind of like the boundary that I'm trying to push. But I agree, like there are many other factors, and I think, like, since I know you're part of some work, right? I think there are many different additional factors that can that are at play here, and it's like complex systems. I guess like you kind of choose how you study it, and I'm not claiming that this is kind of complete specification of the system. Right. Oh.
Before you had an interesting point on the trade-off in terms of accuracy between AI and AI plus explainability. From your insights and your research, what are the typical applications that explainability will really lead to very low accuracy and therefore should not be an objective at least at the current stage?
Actually, like in general, I think like I'm showing an approach where like I actually change the AI model, but I think a lot of the algorithms, for instance, that I listed, they do not change the model at all. So I think like if the concern is that it will reduce AI accuracy, there are like wider class of methods that won't change the accuracy at all. I think the point is more of the explanation that produced are not really useful, or like it's hard for humans to leverage them. So we need to do something different, and I think this alignment, the final part of it, the alignment doesn't have to happen by changing the model. Like you can potentially introduce alignment without changing the model too. I think that's more of a technical design, and you should kind of assume that all explanations will satisfy AI's accuracy. But I do agree, like I guess like similar to this general story, like it seems that RLHF kind of made the large language models a little weaker than the one before RLHF. I think it also in practice happens a lot, but I do think the diminishing in AI performance is usually pretty small. In most cases that I know of, if it diminishes at all. And in many cases, you may be able to do it just without any diminishment.
All right, great. Chenhao, thank you very much.
Thank you.